What? I mean, it's a bat. What's the worst that can happen? Anyway. Hello, welcome, fifth graders. We are starting our physical and chemical changes, lesson 2, mixtures and solutions. Some of the concepts in here is kind of difficult to follow, so what's going to happen is after I'm done and I upload this stuff, I'm going to put this PowerPoint online on my website so that you can follow along a little easier. So the first thing I want you to do is let's go to our science probe, Salt and Water, Be a Scientist Notebook, page 220. I'm going to read this to you. A spoonful of salt has a mass of 10 grams. A cup of water has a mass of 300 grams. What do you predict will be the total mass of the salt water when the salt is dissolved in the water? Circle the answer that best describes your thinking. Is it more than 300 grams? Is it going to be less than 300 grams? Is it going to be exactly 300 grams? And not only when you make a hypothesis, we not only state what we think, but why we think so. So if you give me an answer here, make sure that you write down what was your reasoning behind what you answered. So let me get rid of this. All right, and here we have our scale. So here's our salt. And I'm going to write it down right here that I massed the salt at 10 grams. That's 10 grams of salt right there. Now the science probe wants us to have 300 grams of a glass of water. The beaker with the water, I'm going to put B plus H2O equals 301 grams. Now, my scale right here does not do any decimal points. So if it has 300, 301, 302, about a gram of margin of error. So we just won't kind of worry about that. I need to get a more accurate scale. But it is what it is. We're in quarantine and I was eating a bat. So now I'm going to take this salt, which is our solute, and I'm going to dissolve it in our solvent, which is the water. Put it in. And I'm going to start stirring until it dissolves.
A few minutes later. 1 hour later. 1 eternity later.
Oh, it took a little longer than I thought it would. But anyway, here we have our dissolved salt water. Now, if you can look closely, and you probably can't hear, but you can do this at home, I can see just little bits of salt that are still kind of swirling around in there. So we probably exceeded the amount of salt here that this water can hold. That's okay. That's all right. So now we are going to mass this together. We're going to mass all this together, and we have, of course, 10 grams of salt and 300 grams of water in a beaker. Together, that should be what we have, 311 grams total is what we had if we just added these two things together. But now we don't have the salt in solid form. We have the salt that is dissolved into the water. It's still solid though. All right, now are we going to have 300 grams when I mass this? Are we going to have less than 300 grams when I mass this? Or are we going to have 300 grams on the dot, or 301, or 299, just somewhere around in there? What are we going to have? If you haven't made your prediction, make your prediction. Tell me why. You can pause it because I'm about to do this. You've been warned. That's a second warning. Don't make me do a third warning. I'm just kidding. All right, so let's do this now. Now, to be accurate, I'm going to stick my parchment paper, which the salt was on the scale also because it was part of that first mass. So we got 310 grams, and like I said, we have kind of a 1 gram here or there error, margin of error. So that is 310 grams. Our total, when it was separate, was 311 grams. So I'm thinking that there was probably mass 310.5, 0.4, 0.6, something around in there. So did you get that right? And why or why not? Why do you think so? Well, we're not going to answer that now because you're going to answer that at the end of the unit. So let's go ahead and move on. Scale back over there. Put our salt water right there. Okay, so this is going to be our lesson vocabulary today. A mixture, a heterogeneous mixture, a suspension, a colloid, a homogeneous mixture, a solution, solubility, solute, solvent. Some of y'all should be, we covered a lot of this before we went on break, especially solution, solvent, and solute. Y'all should have those down pretty good, but we're going to go over them just the same anyway. This stuff gets tricky. In fact, there's some of these things that even scientists don't really agree on. And we'll talk a little bit about that. But this stuff gets tricky, so pay very close attention to it. Okay, a mixture. It's a physical combination of two or more substances which remain chemically separated, even though they might not look so. The key word here, physical combination. We've been talking about the physical properties of things. When we look at here at our salt water, and it is cleared up pretty good. Those little bitty particles that I saw floating around in there now have gone to the bottom. But look at the water. It is now very cloudy. But there's salt at the very bottom. Can you see the salt at the very bottom of the beaker? Okay, you can see the salt a little bit at the very bottom of the beaker. That's solid particles down in there. I can actually put my fingers down in there and move the little pieces around. See, they're no longer clumped together. I was moving solid pieces of salt that was still there. So nothing physically changed. There was no third substance formed from this. It's just salt. It's just water. So let's move on. A heterogeneous mixture is a physical combination of two or more substances which are not uniformly mixed. They may appear to be or may not. You may need to have a microscope to determine whether or not these things are. But let's talk about heterogeneous mixture that we can all pretty much agree is a mixture of different things that are physically separated from one another. I'll give you an example of that. Here we have an example of a heterogeneous mixture. Trail mix. Infinitely more tasty than a bat. But here we can see the peanuts separate, the M&Ms separate. Oh, that's good M&Ms. The raisins, separate. Oh, this is good. This is a heterogeneous mixture of two or more things in which their physical characteristics are still there. When I put all these things together, we didn't get a, how's that? This is not a me nut. It's a peanut and an M&M. They didn't chemically form to form a third thing. They're still separate, each one of them having their own separate properties. That is a heterogeneous mixture. Some things, though, may look like they're all one thing. Take, for instance, our salt water. Our salt water is not a heterogeneous thing, but sometimes we can't tell the difference just by looking at them. Sometimes we'll have to know. If I didn't know, for example, that this was not a heterogeneous mixture, I'd have to look at this under a microscope. Some of the things that we have that are heterogeneous mixtures, you have to determine those kind of things. Some of these things are really hard to figure out without the aid of a microscope. So let's talk a little bit of Latin here, because of course Mr. Williams and Ms. Cowan always talk about all of these prefixes and suffixes and these root words that come from Latin. So let's just kind of take a look at these two prefixes, hetero and homo. Hetero means different, and homo means the same. So that's an easier way for you, because you guys already know these prefixes. This would be an easy way for you to kind of figure out what some of these things that are more visual, what they actually are. So let's get back to heterogeneous mixture. A suspension. I had a great idea for this, but it's been raining and we've been quarantined and I have not been able to get the things that I need to show you this, but you can do this at home. What you need is just a beaker of water, just plain water. Go outside and get some sand or some dirt from your yard, put it in there, shake it up real good, sit it on the table and leave it for a while. That is what a suspension is. It's a heterogeneous mixture in which the parts are not easily seen. One or more substances are suspended in the mixture and will settle or fall out. This is cool. Once you get your sand and your dirt and you shake it up and you sit it down in your beaker of water, come back in about 30 minutes, you'll start to see layers of sediment at the very bottom. The heavier stuff always falls first, which is typically, I'm not going to spoil it for you. You figure it out. The water will still be kind of dirty at first, and you'll start to see all these layers of different things piling up on the bottom, and you will see distinct layers. But that is what a suspension is, that the stuff is in there, but it falls out. It is suspended for a little while, but then it falls out, and then it settles down to the bottom. So, muddy water. And here's a colloid. Now, your book is not entirely accurate about this. This is one of those things that I was telling you earlier that scientists still are kind of in a disagreement. Most of them say it's a heterogeneous mixture, so we'll kind of go with that. But sometimes some scientists think that it is a homogeneous mixture. All right. This is the difficult one. If there was going to be one in here that you would have a little bit problems with, this would probably be the one. This is a mixture which all the parts are so small that they do not settle or they do not fall out. A suspension, those particles are big enough that they will fall out of suspension from the water. In a colloid, they don't settle, they don't fall out. Smoke and gels are some examples of a colloid. Matter of fact, peanut butter, it's a colloid. It's a delicious colloid. Look in there. Do you see all the individual particles in there? Do you see all the different things? Look at our, again, look at our definition of both mixture and a colloid. The parts are so small that they do not settle or fall out. And sometimes it looks like it's all one substance, but it's not. Cut that. Here's another colloid that you can actually make at home, but I'm not going to tell you how to make it. Can you see that real well? It's kind of undulating back and forth a little bit. This is stuff that you can find in your kitchen. It's a vapor. It's not smoke, but it's a vapor. Basically what this is it's a colloid with air and solid particles both combining together. I'll take this off and let you see how it kind of floats. But yeah, probably half of you probably have the stuff in your kitchen to make something like this. Look how it looks like fluid. Shoot it from the top. You can see it kind of waving in there. Isn't that cool? That's pretty awesome. I'm kind of blown away by it. That's really cool. Oh, look, I'm pouring it out. Oh, look, I'm pouring it out. Oh, look, I'm turning it upside down. Okay, I'm really having too much fun with this. But that is an example of a colloid. Another example of a colloid that a lot of you probably like, I know I do, and I don't have any with me because, of course, we're in quarantine. Jell-O. Yep, Jell-O. It looks like it's uniform. It looks like it's one thing, but it's not. It's a mixture of a whole lot of different things, and they're not evenly spread out. Even though they may look like it, they're not. That's why I say sometimes it's hard to tell which one of these things is a colloid and which one is not. You have to have, and sometimes, in some instances, you have to have that microscope in order to tell. All right, here's some examples of colloids. And colloids don't have to be solids mixed together. They don't have to be gases mixed together or liquids mixed together. They actually can be a whole lot of different things together. For example, gemstones. And we're not talking about diamonds because diamond is just carbon. But different gemstones are a bunch of different minerals put together to form a gemstone. That is a solid colloid. You have a solid liquid colloid, like starches and waters, a solid gas, aerosols. Basically what I just had, it's all gone now. But basically what I just had here was kind of what you could consider an aerosol. It was solids in a gas. Liquid. Milk is a colloid. And yeah, but after a while when it spoils, then you can start seeing all the solid particles down at the bottom. When your milk gets chunky, Anyway, liquid solid like butter, jelly, fog. We have gas and solid. We have foam. Styrofoam, remember the styrofoam? That was a colloid. Remember I took the gas out of it and it became that little hard piece of polystyrene that you could bang on the table. Basically what I did was I got all of the gas out by dissolving it in acetate. There was still polystyrene that was in the acetate, but the acetate could only hold so much polystyrene, so it fell, the rest of it just fell out. It couldn't be dissolved any further. So I just gathered all of that material up, let it harden. All the gas had already escaped through the air, and what was left over was the solid polystyrene. But if it's in styrofoam, that styrofoam that we know that comes in packing peanuts or whatever, or the box that I dissolved, the box was originally a colloid. All right, now that we know what heterogeneous mixtures are, now we need to know what homogeneous mixture is. Homo meaning same. It's a mixture in which the particles are uniformly or evenly distributed. Salt water, it's evenly distributed. If you look at this under a microscope, it would be even. The amount of salt molecules and the amount of water molecules in any given sample would be the same. That's also the case for sugar water. Is a solution in a homogeneous mixture the same? Well, it's complicated. Solutions are always homogeneous mixtures. This is a solution. It's also a homogeneous mixture. But homogeneous mixtures are not always solutions. Okay, the concept here of solution is reserved to a solid and a liquid. So if you have a solid like sugar or salt and you put it in a liquid of water, that is technically what a solution is. But as we talked earlier, you can mix solids and solids together, or gases and liquids together, or gases and gases together. And those wouldn't be considered solutions. They would just be considered homogeneous mixture. A solution is a homogeneous mixture, but not all homogeneous mixtures are solutions. Air is an example of a homogeneous mixture of nitrogen, oxygen, argon, and other gases in the air. So the air that we breathe, it's not a solution, but it is a homogeneous mixture. Salt water is a solution and a homogeneous solution or mixture. I know this is kind of difficult to process all of this. Just remember, I'll have the notes here online. You can always dojo me your questions about these things. So let's just go back and think about solvent and solute, because we did talk about this before we left for our break. A solvent is the compound, is the component of the solution that is present in the greatest amount. Here we had way more water. We had 300 grams, a little less than 300 grams because the beaker was involved in, but we had about 260 something grams of water. We only had 10 grams of salt. And as you can see, there's still salt at the bottom of it. So we could have used some more water to help us there. So in this case, the solvent is going to be the water. Water is also called the universal solvent. We've talked about this before. Given enough time, water will dissolve practically everything on Earth, with a few exceptions. Almost everything, given enough time. It's usually a liquid. Doesn't always have to be. but it's usually a liquid. A solute is defined as the substance that is dissolved in a solution. In this case, it was the salt was our solute. This should be just recapping stuff that you already know. Solvents can only dissolve so much of a solute before the solvent falls out. In this case, you can see it here. Solubility is the greatest amount of solute that can dissolve in a solvent. So we have exceeded the solubility of the water in this case. And when you do that, your particles will fall out. So no matter how much more salt I add to this, no matter how much more salt that I add to this, it's not going to make this water any saltier. It's just going to fall out at the bottom. We'll wait for some of the... We'll leave that there. Check back in just a few minutes with it as some of the solid particles are slowly falling back down. Okay, so colloids and suspensions are two things that are very, very, very similar. Elsie, shut your bone hole. Thank you. Colloids and suspensions are two things that can be confused. Here's a whole list of different things, and y'all can look at this online. I'm only going to point out a few here. But y'all can look at these online on the PowerPoint and write them down. Typically, colloid particles are small. They're so small, as a matter of fact, where's my peanut butter? They're so small. My hands are washed, by the way. They're so small that you can't tell that this is a mixture of a whole bunch of different things. Tasty, tasty different things. However, suspensions are larger particles. Remember our jar of water and dirt and sand that you will do at home. You shake that up, the dirt particles are a lot larger than the stuff that is made in peanut butter or stuff that is made in gelatin. The particle size is a big difference. We call that falling out of suspensions sedimentation, which is exactly what it sounds like. It sounds like sediment. Sediment is the dirty water that forms different layers of sand and dirt and that eventually over time compact and become rocks. We call them sedimentary rocks. It's because stuff was in a sediment, in a suspension of water. The Mississippi River, not, for me, not 20 miles that way, is a huge suspension of dirt and silt and mud, and it picks that dirt and silt and mud and carries it. Those particles are not homogeneous, they're heterogeneous. Those things are separated, and it will deposit those. And we have floods a lot of times, and every few years we'll have the Mississippi River will flood, and the water will go over the banks to the Arkansas side, and it will deposit a lot of this silt. That's new minerals for the farmland. So while floods are a lot of times really, really bad, some good can come out of them when it delivers new mud, silt that has minerals, and deposits that in that land. The water recedes and that sediment stays right where it is. I'm telling you, go out and you get some dirt and some sand, put water in a mason jar or something like that, shake it up and leave it alone, and you'll see what's really cool. It'll look like rock layers. It's awesome. Let's see, anything else that I need to look here? Now, colloids sometimes will separate just a little bit. Let's take my peanut butter, for example. This is going to be a hard shot for you to see. So maybe you can get a jar of peanut butter at your home and look at this. A lot of times, I think I can do this. A lot of times the oil will separate out, but it takes a very long time for the oil to separate. You see that drop of oil? That's natural. It doesn't mean that your peanut butter has gone bad at all. That's just part of it. You can see that oil dripping. So basically what you do is you just take a spoon and you mix it back up and your peanut butter is just fine. It's all right. A lot of times salad dressings, if you like Italian dressing, or practically anything that you buy in the grocery store that says shake before using, it's probably going to be colloid, because you have to shake it up and then mix it so it'll taste good. If not, then you're just going to be pouring some of the things that separate out on top. Okay, this is a lot of information. So how are we gonna organize all this? Well, here's a chart. We start with matter, all matter. We have pure substances, we have impure substances. Pure substances can be elements, compounds. Element, the smallest unit of matter that has its own properties. That would be what's on our periodic table. Compounds, like water, is a combination, chemical combination of hydrogen and oxygen. Our acetate that we use to dissolve our styrofoam is a chemical compound. It is a pure substance. Happiness molecule, serotonin. It's a bunch of carbons and oxygens and hydrogens and one nitrogen that are all chemically together in one pure substance to form happiness. Impure substances, these are mixtures. Now, in this mixture category, we have two: homogeneous, heterogeneous. In homogeneous, we have solutions, like our salt water. Heterogeneous, we have our suspensions and our colloids, although some scientists disagree and that it should be over here for colloid. But normally, we're just going to say right now, for our purposes, for fifth grade purposes, that it's going to be under heterogeneous. So what is it and why? Here's what I'd like you to do. I'd like you to figure out which ones of these things belong in which category, heterogeneous or homogeneous. And then figure out whether they're a suspension, a solution, or a colloid. All right, now I'm going to do something that is going to look really, really cool. Give me a second to prep. So what I have here is olive oil and water. What do you predict is going to happen? And why? You can pause the video right now and make a prediction. It's your first warning. That's your second warning. All right, we're ready to go. I'm going to go ahead and pour this in, see what happens. Take it from over the side. See how those little puddles of oil are sticking on top of the water. What can you immediately say of a physical property of the oil? I hope you answered that its density is less than 1 gram per mil. It happens to be less than water's density. That's why it's up here on top. Now, hello, come on. Mix together, come on, mix together, mix together, mix together. There we go, look at all that. Good, now it's all mixed together. Wait a minute. What's happening? Take a shot at the top here. What's happening to that liquid right now? So is this a mixture? Okay, well of course it's a mixture. Because the mixture definition, let's go back. Mixture definition is a physical combination of two or more substances in which remain chemically separated. It looks to me like they're chemically separated. There's nothing happening here. There's no heat being given off, or there's no gas expansion or something that you would think that when two things come together they form a third thing. There's nothing like that happening here. This is just a physical mixture. What kind of mixture? Does it fit heterogeneous mixture? Or does it fit homogeneous mixture? Well, it's pretty evident that this right here is a heterogeneous mixture because all the things are separated. They're physically different from one another, but yet this is still a mixture. This, of course, got your oil on top because it's less dense than water, but it's not mixing with the water at all. But what if it did? We'll get back to that in just a minute. So this is a heterogeneous mixture. These two things are physically separated. And no matter how much I stir, it will still be separate. Well, I think I've got a way that we can actually put these things together. It's called an emulsifier. Here's my magic emulsifier. It's magic. I'm telling you, this stuff right here, you can't find this stuff in very many places. I mean, this is just magical stuff that, you know, I have to order online from a thing and get all. Wait a minute. No, you've already seen the label. Okay, it's mustard. All right. Now let's see what happens now. Remember, our oil was sitting on top of the water. I've never done this before, actually. I just think it's cool, though. Well, looky there. I see a lot of oil is still stuck up on top, but see all that oil, all these oil particles up here that are still in suspension down here that are not coming up. There's some really cool stuff going on right there. Well, basically, we're not going to talk about it too much because this is already complicated enough. But this is a different chemical. There's a bunch of different chemicals in the mustard, but one of the things that it does is called an emulsifier. So if some of you want to go ahead and look that up and maybe dojo me why you think the mustard made the oil mix a little bit better in this oil and water mixture, you can go ahead and do that. And these are things that you can do at home with adult supervision, especially using the oil, because oil can be expensive. There's different kinds of oils. There's vegetable oils, there's olive oils, there's canola oils. That's a tasty emulsifier. So make sure that you've got permission to use the stuff if you're going to use it. What is also very cool, and I will tell you what to do, but I'm not going to do it here. I'll tell you what to do. But you can also get oil and water in little food coloring. And once you've mixed it all there together, you can drop droplets of food coloring in there. And don't mix it, just watch it and see what happens. All right. Got any questions? Gee, if I was a fifth grader, I would. There's a lot of stuff that was in this presentation here. Dojo your questions to me. I'll get back as quickly as I can. I will be doing the lab on Be a Scientist Notebook, page 223 through 224. So familiarize yourself with that lab and make your hypothesis already. I will upload that on Friday, and be sure to wash your hands and don't eat any bats, because that would be bad.